The padlock on your locker consists of the integers 0 through 39, and a typical locker combination is a sequence of 3 numbers. Let's say repeats are not allowed, although technically with a combination lock, you can do repeats, but for the sake of argument, we're going to say no repeats allowed. If you try one combination at random, what's the probability that you will guess correctly? So with this, let's think about it. Do we pick 3 numbers and we can just plug them in randomly to a combination lock, or do they have a specific place, a specific spot? Do we do one number first and then another and then a number? Would be a combination of 3, 4, 5? Would that be different than 5, 4, 3 or 4, 5, 3 or 4, 3, 5, right? All of those different combinations, all those different possibilities of them mixing together are not the same when we're talking about a combination lock. Order matters when we're talking about a lock. So why is this called a combination lock? It should probably be called a permutation lock. So we're trying to figure out how many total options, right? This is asking for us to calculate a probability, but we first need to know out of how many total options would we have. So to figure out the total options, we do there's 0 through 39 are our options for numbers, which means there's a total of 40 options. If you count 0 as one option, 0, 1, 2, 3, 4, right? So it's one more than 39, 40. So we have 40 options for numbers, and we're going to do a permutation of 3. So how many different orders can you put them in if you're just choosing 3 of them? Going to probability and choosing permutation, we do 40, 3, and we get 59,280. So it's asking us if we choose just one combination, what is the odds? What are the odds? What is the probability that you will guess correctly? 1 out of all of those different options would be 1 over that number. So if I were to do 1 divided by that number, I get a scientific notation, 69 times 10 to the negative 5. Remember, if it's a negative number there, it means it's a really small number. Since we technically haven't turned it into a percentage yet, I'm going to multiply it by 100 to turn it into a percentage, and I get 0.00169%. Less than half of a percent, right? 1% would be 0.01. No, less than, because we've already turned it into a percent. So it's out of a decimal and it's into a percent. So it's very small, definitely less than half a percent. It's less than a tenth or a hundredth of a percent. So tiny. Really quickly, I would like for you to get out a separate piece of paper, and I want to readdress Pascal's triangle. I hope that in your Plinko activity, you noticed the relationship between the odds of how they play out, especially if you kept the denominators the same for each row, seeing the connection between the probability that we found out compared to Pascal's triangle. So Pascal's triangle is applied in all sorts of different ways, as you saw in our opening video today. And they did mention something about using combinations in order to help you put together the Pascal's triangle. And as they said in the video, sometimes your triangle, if you're trying to find the 16th row of Pascal's triangle, that means you have to go down and do all of that adding and break down the triangle all the way to the 16th row. Or you could use combinations. So if you were to do 16, choose 0, you would get, I think, an error, but the idea is you would get 1. If you did 16, choose 1, you would get the second number. If you did 16, choose 2, you would get 120. If you were to do 16, choose 3, you would get 560. And if you keep going, you will create an entire row for your 16th row of Pascal's triangle. So, sorry about that. So if you were to try and find an entire row of one of Pascal's triangles, if you did your total and then the second number, like if you chose 2, so 16 choose 2, you would get the third placement, or the second number in from 1. And you can create an entire row that way. So that is a way that you can create if you have a missing part of Pascal's triangle and you need to know a specific spot on Pascal's triangle. You could always use combinations to find that specific spot. Okay, so your homework tonight is going to be a general overview of the counting principle, permutations, and combinations. So please make sure that you feel confident and comfortable on what the difference is between all three. So let me do a recap for you before you go to your homework. The counting principle, the fundamental counting principle, is when you have specific spots, so kind of like permutations, where you need to find the number of options for each. But with each spot, you have its own pool to choose from, right? So remember back to the clue example. When I have 3 different spots, I need to pick a person and a weapon and a place. When I pick a person, it's not diminishing from the pool of the weapons or the places. So it's spot oriented, but you have different pools that you're pulling from for each spot. And that's when we use the fundamental counting principle. When you're using permutations, again, specific spots, but you're pulling from the same pool of people. And so that's why factorial comes in, is because when you pick president, you've taken one person away from that pool. And then now you will have one less from your pool of options to do vice president and secretary. Combinations is not spot specific, but from the same pool of people. So the opposite, it's the flip of permutations. So combinations are if I'm trying to pick a group of 3 people to be ambassadors for the 10th grade, then that would be just picking 3 at random. There's not a rank of those 3 people. They are just 3 chosen. And that would be combinations. So that's the difference. If you're still confused, please definitely reach out to me and ask questions, because your homework today is going to ask you to be able to know the difference between them. Okay, good luck.